function include my gain, G omega, and my phase angle. That's my frequent response functions in terms of real value. Alright? And normally, the people use Wi omega, use I omega, also call them that's a frequent response functions. And I don't like that. I like the way I define here. I call it because this is all real number and this has physical meaning. So the gain G omega, that's the gain. Now the amplitude divided by input amplitude, and that's my gain. And then I have a phase angle. So I have a two number that's a G and phi, and that it is those two and phi together will be my frequent response functions. Okay. Alright. I think this is a simple math. So I think I don't need to show you how to derive it. You can just look at that. Alright. This is the gain and phase angle. Look at this curve. This curve gives you the gain, that's W omega divided by omega square A. That's again my gain. That's again my output amplitude. In other words, when I earthquake come in, and we have amplitude. And how much I will excite my building amplitude. That's my output amplitude. That's my W omega. So this is why again, I call gain. Did I gain anything or did I lose anything? So we call this a gain. The gain, for this case, omega is from zero. If omega n is assumed is 1 meter per second, that's on my omega n is 1 meter per second. And this omega n is from system. It's nothing to do with my input. It's from system. My system originally has 1 meter per second. That's my system major frequencies. And my system has Zn, it's 0.001. That means my system has a 0.1% damping. Okay, that's 0.001. So that's we call 0.1% damping. And if you look at carefully at this curve, my gain, do I gain anything? I gain zero. If my frequency is very small. If my frequency is growing from almost zero and go frequency, come down my input frequency. Now I'm talking about input frequencies omega, my input frequencies. If my input frequency come to become 1 meter per second, that's 10 to 0. This is all by log. So gain here is 20 log n over g. So normally we plot by log and also plot this curve with this way, just get a dB. So when our frequencies, if our earthquake frequencies is 1, like this 1, it's 1 here, means my earthquake frequency is the same as my system frequencies. If my earthquake frequency is the same as my system frequencies, what happens? It oscillates. Because it's oscillate, this gain has a peak here. See? The peak. Oh. 假设地震的频率跟我的系统的频率是一样，那就是共振。If they oscillate, means in the gain here, dB, means I have a peak. Okay. See? I gain a lot. Gain 20, gain 25, gain 30, gain 40. To 40 means what? 40 means 100%. I have 100% gain. Well, that's a lot of gain. Alright? So, you don't want to do that. But unfortunately, I have only 0.01% damping I have no choice. I got about almost 30 dB. But when the whole square frequency, my input frequency is going up and up and up again, my gain is going down and down and down again. So my system frequency is much more than my input frequencies, then my gain will become negative. dB, in terms of dB, will become negative. Alright. And my low square frequency is much lower than my system frequencies. My gain is also small, it's almost zero. So if this curve has the properties, that means if you don't oscillate, the input frequencies and the system frequencies, they are not the same. They will oscillate. Then the gain will be small or even negative. Alright, that's a gain. The phase angle, if you look at this carefully, the phase angle is very interesting. Phase angle is almost zero, and the phase frequency is small. And then if you come down to about 1, if you look at very carefully about this neighborhood, across to 1, then the phase is going to go up quickly and then change to 180 degrees. That's because this. If you look at this to the formula, the denominator, 1 minus omega n. When omega less than omega n, what happens? Then this denominator is plus sign. Right? That's simple. If omega less than omega n, 这个分母是正的。If omega larger than omega n, 那分母是负的。So, we change because of the sign change of the denominator for omega. If omega smaller than omega n, this sign of denominator is negative. When omega larger than omega n, this denominator is positive, is negative. Yeah, it's negative. Omega larger than omega is negative. So it becomes 180 degree phase. So this become positive is 0 and negative 180 degree equals 0. But there's a changing here. It's not just changing at this point, but changing slowly at this point, because this is 10, this is 1, and this is minus, this is 0.1, and so there's a changing from here, and sharper up to 180, and then flat. So this is the property of the frequency response functions. Your phase will change from positive to negative at the point of your natural frequencies. The phase here change at this point. That means 1 meter per second. And your gain will be the maximum at the point of your natural frequencies. Right? So this is very easy to see. And this is with the harmonic input. So that's my frequency response function. If you look at this, I say 30 dB is 100. You know why? Because if you have G is 100, log 10 100 is 2. 2 times 20 is 40. So if Z is 100, that means 100 times 100. Gain is 100. If your input amplitude is 1, your output amplitude will be 100. That's terrible, right? What's at last? The changing at 40 dB. 40 dB means my amplitude, my input amplitude, if my input amplitude is 2, my output amplitude will become how much? 200. 100 times change. Your amplitude your earthquake amplitude is only 3, then your building amplitude will be 300. Did you worry about it? I do. So, you want to have a dB as small as possible, never be negative, like negative, or negative 20 and negative 40 is another, that's a different meaning, but at least you want to be close to 0, right? That's good. My gain is 0 is good, right? I don't have any gain. Okay, so that's the way we do, but there's another way to plot it. This is a different way to plot it. And if you look carefully here, I have also log in the x-axis. This one I don't have log. This one I have to say different plot. So this one become here, and this doesn't matter. I think you don't need to do that. But anyway, that's a different way of plotting. Some people like to have this way of plotting, and some other people like the plotting in the previous slides. Okay, now let's look at this case. Now we have a more spin and more dead spot. When I have more spin and more dead spot, then I expect to have a nature frequencies low. So if you look at this carefully, I have W1, I have W2, and the previous case I have only 1 W, and now I have 2 W. When I have this 2 W, then what happens? And I want to look at my frequent response functions. And this is the way to derive the equation motion. I will spin force from K1, I will spin force from K2, I have spin force from K3, so I have these spin forces. I have a dead spot force from 0, 1, I have dead spot force from 0, 2, I have dead spot force from 0, 3, and we will have two forces. With spin force and the dead spot force, and the Newton laws give us the whole equation of motions. And this is the way we derive the spin and dead spot system. By the way, the building, like 101, you can derive this way too. If I assume that 101 has a 1,000 spin and 1,000 dead spot, you can do that too. In matter of fact, in engineering, we model the high-rise building with just like this spin and dead spot system in terms of finite element. We call finite element method. Okay, now this is just important for a dynamic system. But now, for 2-degree freedoms, I want to talk about 1-degree freedoms. I want to talk about 2-degree freedom so that you can have a good feeling of frequent response functions. Because that's the way, again, we tell the people how my control design, how good or my control design is. You can express it in terms of your frequency.